Right, let's go. Then we can go to the pub. Right, hi everybody. I'm Phil. If you haven't met me before or you're not aware of what we do, we are the sponsor for today. That means I get to blather on about some product that we do. But I'm going to try and make it slightly more interesting by I'm going to tell you what we do in this scenario within our products, but also give you some stuff that you can take away if you are at all interested in content distribution over Wi-Fi. There's lots of stuff that you can do, lots of stuff that you can consider to kind of make it work better than it might be doing. So we shall kick off without further ado. So what we're going to cover is the old problem, the new problem, Wi-Fi and multicast. Is it bad? Is it good? What do you do when you have to talk to the network folks? And as I mentioned, some solutions that you can take away, whether that's from us or just stuff that you can do out of the box. So this first slide, this is the problem that we've been trying to solve since forever. And the space that we're in is all around content distribution, and historically it was all around branch offices. So you might have a head office with a data center, tons of branch offices, some campuses, but really it was all about, as Rob was saying, it's almost over time becoming a legacy problem in that you have links all over the place that cost lots of money. And it's still the case in a lot of our customers. So it's about managing those links, and it's about using peer-to-peer technologies. We work with the Microsoft peer-to-peer technologies, so we work with branch cache, delivery optimization, config manager, peer cache, to try and alleviate those problems. And that's kind of the traditional space that we've always been in. But then in recent times, so I would say in the last year, we've spent the last year really focusing on what happens in Wi-Fi scenarios, and that's because what we're seeing more and more of is companies going Wi-Fi everywhere. So putting in Wi-Fi on campuses, even just companies just spinning up an office, they'll just put Wi-Fi in because it's easy. And Wi-Fi can vary massively depending on the quality of kit that you put in, and lots of other factors. So customers that were successfully using peer-to-peer technology to kind of distribute software were coming to us and saying, oh, these networks over here are really, really slow and users are not getting a great experience. Why is that? Because we're using peer-to-peer. So we started looking at it in quite in depth, and I'm going to share what we found. And the bottom line is, as with a lot of technologies that we work with, it's complicated. But there are a lot of things that you can plan for. There are a lot of things that you can use to mitigate the issue, depending on your individual scenario. So we're going to start off with a bit of a summary in a way. Wi-Fi is great because you can walk down the street here and you can connect to a Wi-Fi network in a pub or whatever. There's open Wi-Fi, and it's great for just kind of users just doing stuff and getting good connectivity and maybe downloading something. Where it can be slightly problematic is in a scenario where you have a point-to-point connection between two machines on a Wi-Fi network. So everything in that scenario, and they need to move something around, then everything has to go through the access point, right? Where it gets even more tricky is where you have subnets that span many, many access points and maybe even physical locations, which we do. We have some local government customers that have massive subnets. So they have massive address ranges that span multiple locations just because it's easy for the network team to configure it that way. But the downside of that really comes into play when you're in a mass deployment scenario. So on Patch Tuesday, the problem is that there's just too much point-to-point traffic going through the access point, and you have what we call AP meltdown, access point meltdown. So the thing with Wi-Fi is it's all about airtime and it's about available airtime. And these are sort of finger in the air, current sort of recommended, comfortable levels for data and for video and for voice. So recommended is, 70% free, your maximum usage of airtime. Anything above those percentages, then that service starts to deteriorate. So with data, basically, you start to lose a lot of packets. With video, you start to get a lot of jitter. Within voice, you lose a lot of quality in your voice calls. So what we did was we set up a wireless network to emulate what our customers are doing. And what we found was that anything that uses multicast is a Wi-Fi killer, can be a Wi-Fi killer. So just a 400 kilobit multicast mass deployment we found was taking up to 80% of airtime. That's not even the content distribution itself. That's just the multicast traffic. So that's what was causing all the issues at our customer sites that we're using branch cache, for instance. So you've got multicast traffic, you've got unicast traffic, and you've got free airtime. You can see there's not much free airtime in the test that we did there. So what can we do about it? I mean, the other villains, there are other villains on there as well, other things that cause this kind of issue that eat up the airtime, things like other users of multicast, things that discover services, so Apple, Bonjour, etc. A thing called DNSSD, which is in Windows, which is used for discovering things like printers, etc. That can all impact the airtime on the network. If you just take multicast out of the picture, then the problem mostly goes away. So that's point number one. But it's not quite as simple as that. There are other factors that play into it, and part of it's down to, for instance, the numbers of users per access point. If you've got an access point and you've only got 2 users, well, there's no problem. You can play all day. If you've got 20 to 30 users on an access point, then it can be not great. If you're doing a mass deployment, that's when things can start to deteriorate. And this is just really illustrating the issue, because a lot of people don't really understand why this can impact things so badly. And what it is really, if you think about the content, it's coming down from maybe a distribution point or even from the cloud. The bit in yellow there is your multicast traffic. So the white is your unicast traffic, and that's a straightforward HTTP transfer. So you've got stuff coming down from the distribution point, from your content source. You've got all of this multicast traffic then saying, okay, who's got this content? And then, even if you can find the content, what you've then got to do is to transfer that from point to point. So again, it's come down from the distribution point, it's gone through the access point, and then it's got to go between these 2 endpoints. So it's got to go through the access point again. So what you end up with is the access point just can't cope. So what multicast does is basically it takes away airtime from unicast traffic, which is the bit that we want to protect. There are things that, modern day access points, newer access points, you have a thing called a fair, it's almost like a fair usage where it splits airtime equally. There are things you can do to kind of protect or prevent this unicast storm. You can just disable unicast. A lot of companies do that. But that causes other issues. If you're trying to use branch cache, generally speaking, and it's turned off on some subnets, then you're almost in an even trickier scenario, because then everything has to download the content. There's no content sharing, and you can still end up with your access point being overloaded. So that's branch cache. other peer-to-peer technologies that we work with and the way that that behaves with wireless, slightly better. I mean, peer cache works pretty well with wireless. That's config manager peer cache, because obviously it doesn't use multicast to try and find other clients. It uses a lookup to the distribution point. So you instantly doing away with that multicast storm. But it's not really great for the primary users of Wi-Fi, which are laptop users, right? I mean, a lot of people where Wi-Fi is widely used, it's where people are coming in temporarily maybe, and they just want to get onto the Wi-Fi and do their work. And these types of users, peer cache isn't great because it's not so dynamic. So delivery optimization, which is the newer Microsoft peer-to-peer technology, although it mostly doesn't use multicast, it's kind of might do one day, but I'm not allowed to tell you about that. So,
can I just ask a quick question?
yes.
This is a scenario that I'm currently experiencing, but does it corrupt the data? Because if I think of like branch cache as like a torrent in a way, I guess.
Yeah.
So would it feels to me on some devices that the updates have been failing or incomplete, or there's data corruption, it's failing to download an update, for example?
Well, it's a good question. So what is the actual effect on the download? Well, most of the time the effect, if you're using branch cache, most of the time the effect is just that you don't get any peer-to-peering.
Okay.
The reason for that is that the discovery packets that branch cache sends out, they have a TTL of 1. And if that's got across multiple APs and if there's a big multicast storm, then they just don't get a reply. So clients are looking for content constantly and they never get a reply. So they end up going back to the distribution point. It shouldn't really end up with the corruption of any content. I mean, you might get hashing issues occasionally in really bad scenarios, but mostly it just makes it really, really inefficient because branch cache kind of has built-in checks and balances. Okay. And what it does is it basically, if it's getting content from a client and then suddenly it gets a bad packet or starts missing packets, it goes, okay, I'm going to ignore that guy for the next 5 minutes. And eventually it does that to everybody, so it stops looking for content.
But therefore I could set a rule when I pre-cache, I could say a desktop hardwired, not Wi-Fi.
Yes, that's a very good point, and that's what most of the solutions to this revolve around that kind of scenario. Because usually when you've got Wi-Fi, you've got a wired network pretty close by. So for delivery optimization, the main reason that can be bad for Wi-Fi is that it's just really fast. So it's the actual transfer of the content itself. So we still get access point stress because branch cache is kind of limited to about 60 megabits per second peer-to-peer. Delivery optimization will just go as fast as the network will allow it to. And that, in turn, all has to go through the access point. So if I give you a real-world scenario, we have a lot of schools and universities that use Wi-Fi in their classrooms, and they do a lot of streaming. They do a lot of their classes involve streaming educational content. If a mass update happens to kick off in the middle of that, then the content stream just dies. It just goes all jittery. So it's not great. And it doesn't take much. It only takes a few machines to start trying to peer-to-peer a cumulative update, for instance, to bring things down. Microsoft are aware of this. We speak to the DO team quite a lot. They are looking at ways to detect when they're on Wi-Fi and behave better. Recent releases, I think as of 1809, delivery optimization now uses LEDBAT on the peer-to-peer connections. The issue is that if it's if it's a very small segment, there's not enough latency to push the connection into a lead-back state. So lead-back never kicks in until it's too late. So other things that you might find from a network perspective, it's not just all about multicast. So a lot of network teams are aware that multicast can cause issues on Wi-Fi, obviously, so they just turn it off. Firewalls can block multicast traffic. Which obviously stops the issue of the access point being impacted by that multicast traffic, but it means then that there's no peer-to-peering and everything has to come from the content source, which is still can be almost as bad in a mass deployment scenario. There's a thing called central switching, which is a Cisco thing mostly, and it was kind of popular. It's not so much now, but it's in place in a lot of places. And what that essentially means is you have a remote location that has Wi-Fi, but there is no peer-to-peering possible because every packet goes back to the wireless LAN controller, they're all centrally managed. So they all sit in the data center. So even if it's on the other end of a WAN, every packet goes back to the data center. So there's no peer-to-peering whatsoever. There's no peer cache, there's no delivery optimization, there's no branch cache. And we're working with a customer at the moment. They have over 40,000 endpoints in this scenario. And they want to use peer-to-peer to try and take the load off the distribution points, but because all of the packets are going back to the data center, it's just not going to fly. They're just not going to gain anything whatsoever. In fact, it's probably going to make things worse if they do enable all of these peer-to-peer technologies. And it can be quite hard making the case because the network team will just turn around and go, well, multicast is just going to kill the access points. So what you need to do, you need to be quite diplomatic in your approach. And so now we're going to move into the good part. And that's been a lot of doom and gloom about what can go wrong and what does go wrong. So I'm just going to talk a little bit about what you can do about it and how we deal with it within our products, because our products are all about trying to deliver content in a way that doesn't impact the end user. So what we have a product called Stifler, which is basically takes all of these Microsoft technologies, takes branch cache and peer cache and delivery optimization, and it doesn't really matter whether you're using Config Manager or Intune, WSUS, or Windows Update for Business. All of this content, we kind of glue it all together and make it work in a kind of friendly manner, but a very efficient manner. So over the last year, this is kind of the stuff that we've done to alleviate this issue. So because we have an agent on every machine, we can detect if it's on Wi-Fi. So we know things like the access point it's connected to and the signal strength. We know which channel it's trying to use. So based on that, we can make some intelligent decisions. So the first thing we do is that we stop branch cache from transferring at 60 meg per second between endpoints if it's on Wi-Fi. So if it's on Wi-Fi, we limit it to 1 megabit per second. Well, that means it's pretty slow, right? But that means you can still peer-to-peer, and it's all going in the background. But the main thing is that, in turn, drops the amount of multicast traffic. So by dropping the transfer speed right down, that means that there's not as many multicast packets going out as quickly. So it keeps the airtime usage down to a level that's tolerable by the access point. The other thing that we can do is that we use the Windows QoS, and we can prioritize traffic. Not many people use the QoS kind of policies that's built into Windows. Anyone here using them? No. They actually work okay. And they're there, they're available to use. You could do that yourself manually. It's just a policy. Next on the list, we can now do per access point peer-to-peer. So in that scenario where I said it's bad to span all of these access points, you might have a single subnet that spans 20 access points. We can limit that per access point because we know the SSID. We can create peering groups so that peers will only peer with other peers on the same access point. So that means that there's more chance of your branch cache discovery packets getting a reply. The other kind of tweak that we do is that we make sure that the machines with the highest signal are the ones serving the content, because that means that they've got more chance of actually being successful in serving out that content. So if you've got a laptop right on the edge of the Wi-Fi kind of range, and their signal is only 20%, you don't want that. You don't want them serving 20 other peers because they'll soon get swamped. So we make a decision on that, and we say we'll only allow peers to serve content if they're over 75% signal. If it's lower than that, all we do is simply we block the inbound requests. And if they don't get a reply, then they'll never participate in that peer-to-peer conversation. And we have a new green leader role, which I'll talk about in a minute. In terms of visibility, one of the things that we do, we've introduced some new dashboards. So we now do a Wi-Fi heat map. And this gives you an instant view of your network. And what you get is each of these squares have a number. They're all 0 because this is just the lab environment that I've got at home. But what you get in there is a little number, so you know exactly how many clients are in each of these squares. And obviously red is they're the ones with the lower signal strength. So the network guys quite like this because it tells you a lot of information. What you can't really see very well there is, which is a bit blurred up by where the donut is it tells you what type of Wi-Fi, whether it's N or G or AC, for instance. So you can see the split of all your clients. You can see how many access points we've got, how many clients per access point. We've got one customer who's actually just built a new office, and it's a massive, massive office, and it's for like 5,000 users. And they put all new kit in there, and they've mandated an access point ratio of 1 access point per 2 users. So you might need to wear your tinfoil hat when you go in there, but I mean, you get great connectivity, right? So, but that does have a big bearing on it, you know. So if you spin this up and it says, okay, your AP client ratio is like 20 or higher, then you're in dodgy territory. So it's quite a good indicator. No, let's duplicate a slide that crept in there. So the other thing that we do is, and what you can actually do manually as well, you know, this is just what we do within the product, but we have the concept of a green. So just quickly explain how our stuff works. We have the concept of a red leader. So if you have a subnet of 20 machines, we select one machine that we think is the best candidate to be doing the downloading and sharing that content out. So he's known as the red leader. That's been like the traditional branch scenario. What we've got in the latest versions is that we've got the concept of a green leader, which flips branch cache into something called hosted cache mode. That means there's no multicast involved. And ideally, that machine will reside on a wired network that has access to the Wi-Fi network. So what that does basically is cuts out the multicast. So we remove the multicast by flipping it into hosted cache mode. And we tell all of the clients that they're in hosted cache mode. They don't do a multicast discovery. We give them the name of the machine that's the green leader, and they do some direct querying of that machine. So there's no multicast. We dynamically choose, you can nominate a machine, but we dynamically choose desktop class machines that are on a wired network for that role specifically for this purpose. So we kind of do it in a hands-free manner. But what that does, it works really well, and we found that it reduces airtime usage by about 50% versus using branch cache in a traditional multicast scenario. This slide makes me laugh. I did not make this slide, by the way. This is done by a very, very technical person. Okay, I'll be asking questions on this in the pub, right, so pay attention. Your beers might depend on it. So this is how a hosted cache mode has been around forever in branch cache. It's just not very popular. So what we've done is we've used the branch cache APIs to kind of turn it on its head, use it in a client scenario, and this is how it kind of works. So you've got a branch office, or any office really, with some Wi-Fi. You've got a red leader, but we've elected a green leader. And he's the guy that's going to act as the hosted cache server, if you think of it in terms of server, right? So this guy is going to request some content. He gets the ID. He then does a search for the hosted cache. There's no content there. So he gets the content from the distribution point. He then offers that content to the green leader. Green leader goes, thank you very much, I'll have that content. The red leader then puts that content onto the green leader. The green leader now has the content, so he can serve it out to everybody else. Following so far? Good. Right, next guy comes along. He goes to get the content, he gets the ID. He then does a request directly to the green leader, so this is not multicast, right? And the green leader goes, yeah, I've got the content, there you go. Simple. So there's no multicast, it's all very straightforward, and your Wi-Fi gets to live another day. So that's the branch cache side of things. That's how we deal with branch cache. What you can do in your own networks, if you've no interest whatsoever in buying our product, then you can actually use Config Manager peer cache in a similar kind of way. So what you do in that scenario is on your wired network, you put your peer cache super peer, and you preload that with your content. So you distribute your content to your peer cache machine, and providing that your Wi-Fi based subnets have access or can reach that wired network, then once again, we're not using multicast. So we're doing away with that multicast because peer cache doesn't use multicast. Peer cache will just go, every client will go to the distribution point, it'll do a content lookup, and it will, the management point will return the name of the super peer that they're going to get the content from. So again, we're freeing up airtime, so we're all good. So that is quite a good solution. If it's at all possible, that's the way to go. With delivery optimization, there is no multicast at the moment with DO, so that's pretty good for a start. But as I said, it's really, really fast peer-to-peer. So another way around that, to avoid as much peer-to-peering, is to have your Doink server as close as possible to your clients. So if you've got a building with lots of Wi-Fi and you've got a distribution point, enable Doink on there so that they're all getting the content from the cache. There is still a little bit of peer-to-peering goes on, but nowhere near as much. So you will find that it does behave a lot better. I mean, Doink is a pretty useful kind of technology anyway. It sits on the distribution point, so if you have a distribution point, and this is available in 1906 only at the moment, then all you do is check the box to enable it, and your clients will be automatically pointed to the correct Doink enabled distribution point. So it's fairly straightforward, but it's the same concept. It's avoiding the kind of peer-to-peer storm on the Wi-Fi network by doing point-to-point connection to a wired network outside of your Wi-Fi locations. Okay, Has that made sense so far? So this is really a summary, because you can take these slides away, obviously. It's something to take home if you suffer from insomnia. Things to bear in mind. If you only have a few clients per access point, then you're pretty much good to go. It's only when your number of clients per access point hit a certain point, and that in some ways depends on the kit. Like older kit can't host as many clients per access point as newer kit tends to be much better. Newer access points, there's some access points coming out now that even have little caches built into the access point, so it can behave a bit like a caching proxy. If you're in that scenario, if you're lucky enough to have lots of access points and not too many clients, then you're fine. The network can pretty much take it anyway. If your links are good, skip branch cache on laptops. So if you've got great links, we historically always said just enable branch cache everywhere, because it's going to work well in your branch offices, and it's going to offload some of the load from your distribution points in your head office or campus locations. But what we're saying here is feel free to disable branch cache on your Wi-Fi networks if you want to. And you could do that using a CI, for instance, in Config Manager, because you can, with a bit of clever PowerShell, you can detect whether the machine is on Wi-Fi or not, and you could have a CI that runs and just disables branch cache on that location. Use desktop peer cache machines, as I've mentioned, to serve your Wi-Fi subnets. Consider hosted cache mode. It's technically not supported with Config Manager out of the box, but I spoke to the Config Manager team a couple of months ago, and they said, well, the only reason for that is because they just didn't have the bandwidth to test all of the scenarios. So historically, they just said, oh, we're not supporting it. So they're looking to change that, hopefully in the near future. In delivery optimization terms, then use Doink if you've got the opportunity to, because it works pretty well, either on a Wi-Fi or non-Wi-Fi networks. It's a pretty good technology. And I will say, just on the delivery optimization side of things, it really is coming into a lot more scenarios. So like in the latest technical preview, delivery optimization is used for all Windows updates. So it's a good technology to be aware of and to get to know how it works and how to configure it, because in the next kind of 12 to 18 months, it's going to be responsible for everything within Config Manager. It's going to be responsible for packages, applications, Windows updates, and beyond. Diagnostics. If you want to do some testing, we have a free tool called BCMon. The way that works, there's a little YouTube video there with Amy that works for us did to explain how it works. You have two machines on a subnet, and you run it on like machine A, you run it in listening mode, you run it on machine B, and that sends out some branch cache discovery packets. Well, that will instantly tell you whether or not branch cache will fly on that network. We did some work with a customer recently, and Johan Arvidmark actually automated it all using run scripts. So what it does is finds every subnet that's got more than 4 clients on it and runs these scripts in an automated manner, puts the results on a share into a CSV, and so you can. And what we found was that, and this was a 50,000 user organization, we found that 99% of their networks had multicast disabled. So they wondered why their branch cache wasn't branch caching. So that's something that I'm going to blog about that soon. Either I will blog about it or Johan will put it on his blog. But that's just something that you can do really quickly if you're interested in getting branch cache up and running, that you can find out if it's going to work, or if not, why not. And that's it. We've got more to come. We've got one more session from Adam, and then afterwards we're going to go to the pub, and 2 pints is going to buy everybody 2 pints. So, and we've got a giveaway as well. We've got a drone to give away, which is pretty cool, with a little HD camera that you can control from your smartphone. So you can go home and play with that. You can scare your neighbor's cat or close Gatwick Airport. It's up to you. But thanks for listening. It's been a really useful day. I think there's been some thought-provoking stuff from all the speakers. Hope you've had a good day, and hope to see you next time. Thanks very much.